This video, we will find the Maclaurin series of the following function, but not from scratch by finding the higher derivatives, but instead building on our knowledge of the Maclaurin series of e to the x. So recall, e to the x is the sum from 0 to infinity of x to the n over n factorial. And this is true for all values of x. So for every real number, e to the x is equal to this infinite power series. Because this equality is true for any choice of x, well, to obtain the series expansion of e to the 2x, we can make a substitution, replacing x by 2x. The question is now, how do we handle a subtraction from a power series? If we only write down this minus 1, it may seem a bit cryptic how to handle this expression, but things will become much clearer if we expand the first few terms of our series. So we have e to the 2x minus 1 being the numerator of the original function. And as I've just said, let's expand the first few terms. So we'll first write this concisely, and then we will expand. And again, it's not clear what to do with this expression. We have the power series expansion of e to the 2x minus 1. Now, how do we absorb minus 1 into the closed form of the series? And can we do this? Anytime you add or subtract from an infinite series, and you ask, can I compress the expression into a single summation? The answer is, if yes, it will become apparent if you expand the series. Let's expand the first few terms. So when n is 0, we have 1. When n is 1, we have 2 over 1 factorial x. When n is 2, 2 squared over 2 factorial x squared, and so on, and then minus 1. And notice that the first term of the series is 1, so this will simply cancel the first term of the series, and every other term in this infinite expansion will be left unchanged. So this is exactly the same as the original series. The individual terms are not changed, but there is one difference. Instead of starting at n equals 0, we are now subtracting 1, so we are losing the first term, and so we are left with everything else after 0, therefore n starts at 1. And that is the effect of subtracting 1 from the Maclaurin series of e to the 2x. 1 being the first term, we subtract 1, and so we cancel the first term, and so every other term is left unchanged, and so we begin at 1 instead of 0, because we have lost the n equals 0 term. And so now we have the Maclaurin series of e to the 2x minus 1. The only thing left is to divide by x both sides, or multiply by 1 over x. So let's multiply by 1 over x on each side. On the left, this will give us the original function. On the right, we have 1 over x times the right-hand side, the infinite series. And since with respect to n, x is a constant, we can bring 1 over x in as a multiple of the individual coefficients. And of course, pairing up the x with the x to the n term. This will of course simplify to x to the n minus 1. And we could stop there, right? We have now the Maclaurin series expansion for e to the 2x minus 1 over x. This was our objective, but it would be nicer to have here a clean x to the n instead of an x to the n minus 1. So now we do a simple translation. So again, to have an n here instead of an n minus 1, we have to translate n up by 1. We have to add 1 to n to cancel this negative 1 here. So we will get, if we focus now on the individual terms, again translating n up by 1, so we are replacing n by n plus 1. So we have n plus 1 here, n plus 1 factorial, and I will write it unsimplified, again replacing n by n plus 1, n plus 1, minus 1. And now we have to be careful, right? We have translated up the index of the terms up by 1. To cancel this translation, we have to shift down the bounds of summation down by 1. So 1 minus 1 is 0. And infinity minus 1 still infinity. And now we can write the simplified version of this, which was the objective. N plus 1 minus 1, n. And so we have now the Maclaurin series of e to the 2x minus 1 over x, not by finding the higher derivatives of the function, evaluating at 0, capturing the pattern and simplifying, but much more efficiently by building up on knowledge of a simpler, previously derived Maclaurin series. Now the crux of this problem again is if you ever are adding or subtracting terms from an infinite series, in closed form, it may not be obvious to see how the series can absorb the extra terms, but if you simply expand out the first few terms of the series, you may see how the addition or subtraction of a few additional terms may affect the result. In this case, subtracting 1 simply cancel the first term of the series, and so instead of starting the sum at 0, we start the sum at 1. At the very end, we did a very small aesthetic improvement, translating n up by 1 to get a nice x to the n, but to offset this change, we have to translate the bounds down by 1, and so again, instead of beginning at 1, we begin the series at 0. This is the nicest form of the final answer. And that's it.